All right, lesson 10-2. Here's something you already know. You know that the square root of 9 is 3. I know you don't need a calculator for that. And you know why the square root of 9 is 3. It's because 3 times itself is equal to 9, or 3 squared is equal to 9. You know square root of 16 is 4 because you know that 4 squared is equal to 16. And then you've also learned that the square root of 11 is somewhere in between 3 and 4, because 3 squared is less than 11, 4 squared is more than 11. So the square root of 11 must be somewhere in between 3 and 4. You know that without a calculator. But you also know you can put square root of 11 into your calculator. The calculator will give you approximately 3.32. But did you know that the decimals in the square root of 11 will go on forever, and they don't ever repeat? It's not a repeating decimal. Okay, so you cannot write the exact value of the square root of 11 in decimal form because the decimals go on forever and they never repeat. It would take you forever to write square root of 11 in decimal form. You'd never be done. So how do we write the exact value of the square root of 11? Is there a way to do it? Well, the answer is yes, there is a way to do it. And here's how you write the square root of 11 exactly. Like that, square root of 11, okay? When a mathematician wants to write the exact value of a square root of 11, that's pretty much the only option that we have, okay? There is no simplifying that number without destroying the precision of it, the accuracy of it. As soon as we change it into a decimal, we're going to have to throw away some decimal places, really most of the decimal places, and then we have only an approximate value of the square root of 11. So there is no way to simplify this without throwing away the precision. And really, for mathematicians, simplifying, really, for a mathematician, the word simplify carries with it the requirement that you preserve the accuracy of the number, the precision of the number, okay? Changing 1.6 repeating to 1.7 is not simplifying for a mathematician, okay? That's rounding, and that's a different issue, all right? Now, here's something else you probably don't know. Radical numbers have some things in common with regular numbers. Not all things, but some. In particular, they can be multiplied just like regular numbers. And as shown in the example below here, 3 times 2 is 6. The square root of 3, the exact square root of 3 times the exact square root of 2 equals the exact square root of 6. And you can verify this with your calculator, at least to as many decimal places as your calculator will show you. If you punch in square root of 3 times square root of 2 equals, you'll get some decimal number with about 8 or 9 digits past the decimal point. And then if you punch in square root of 6, you'll get the same answer right out all the way to the end of the screen. Same exact 8 or 9 digits. Now, you can't verify that the rest of the digits are the same, okay? But mathematicians have other ways of knowing and being able to prove that the square root of 3 times the square root of 2 really is the square root of 6. So, what are simplified versions of these expressions here? You can multiply square root numbers just like you can multiply whole numbers, but you get another square root answer. So, what's the square root of 6 times the square root of 5? Come on, most of you can do this in your head. You don't have to reach for a calculator. Come on. Square root of 6 times square root of 5, square root of 30, okay? And square root of 30 is, that's not a nice whole number. So that's just it. That's our simplified answer. 7 times 10 is 70. 70 is not a nice number that you can take the square root of and get a nice whole number answer. So that's it. It's as simplified as much as we can. 3 times 12 is 36. But if I asked you to simplify square root of 3 times square root of 12, you wouldn't want to stop at square root of 36. Okay? I mean, that is simplified, but it's not completely simplified because what is the square root of 36? Come on, you know a whole number times itself. is equal to 36, right? And that number is 6. So that would be completely simplified, right? And I am interested in, and I will insist on, completely simplified answers to questions. So if I give you an expression like square root of 3 times square root of 12, and you write square root of 36 and circle it, it just gets marked wrong, okay? It's accurate, but it's only partly simplified. Square root of 5 times square root of 5, you can multiply those together and you get square root of 25. But don't stop there, because what is the square root of 25? It's a nice whole number, right? So you want to give me 5. Who knows their times tables? What's 11 times 11? Right, 121. Good for somebody out there who still remembers. Now, what is the square root of 121? Does anybody know that? Well, come on, it's got to be 11, right? Because how did we get that 121? By multiplying 11 by itself, right? Now, can anybody do 73 times 73 without a calculator? Stop. If you're reaching for the calculator, stop. Can you do it? Probably not. You know what? I can't either. But you know what else? It doesn't matter. I know what the simplified version of this expression is, and you ought to be able to tell me also without a calculator. Look, let's go back to the last two examples. The square root of 5 times the square root of 5 turned out to be 5. Square root of 11 times square root of 11 turned out to be 11. Guess what the square root of 73 times the square root of 73 turns out to be? 73. No accident, right? Because again, think about what we mean by the square root of a number. What do we mean by the square root of 9? We mean the number that when you multiply it by itself gives you 9. Okay? Whatever it is. Well, it happens to be 3. Okay? So what do we mean by the square root of 73? Well, we mean a number, whatever it is, that when you multiply it by itself, you get 73. Okay, so you don't have to go through the multiplying to get the final answer here, right? You should be able to do that without a calculator. All right, and then here is a logical extension of the fact that we can multiply square root numbers together and get a square root answer, which then sometimes can be simplified back to a whole number, right? We can also factor square root numbers, just like we can factor whole numbers. 10 can be factored into 2 times 5. Square root of 10 can be factored into square root of 2 times the square root of 5. And so let's take another number like square root of 12. That could be factored into square root of 2 times the square root of 6, or the square root of 3 times the square root of 4. But hey, if we factored the square root of 12 into the square root of 3 times the square root of 4, and then we focus on that square root of 4 and ask ourselves, well, hey, what does the square root of 4 simplify to? It simplifies to a 2, doesn't it? So the square root of 12 is equal to the square root of 3 times the whole number 2. These two terms are being multiplied together, square root of 3 times 2. Recall that the order of multiplication does not matter, and so I'm going to turn these two terms around, write the 2 first, and then times the square root of 3. And then I'm going to rewrite that expression again without the multiplication symbol in between the 2 and the radical 3. This is just like writing 2x without a multiplication symbol in between, and you understand that that means 2 times x. By the same token, you've got to understand, recognize that 2 radical 3 means 2 times radical 3. Now, here's the reason why we prefer as mathematicians to rearrange the order of the terms so we have the whole number in front and the radical term last, because we want to avoid the potential confusion when somebody might write something like this. Suppose I ask somebody, write down square root of 3 times 2. But, don't bother with the multiplication symbol. They might write down this, square root of 3 times 2. Now, besides the fact that the 2 itself is so sloppily written by me, what else is problematic and potentially confusing about what I have just written down? You can tell, can't you? Like, is that 2 under the square root symbol or is it not? Because it matters. If it's under the square root symbol, then what that really says is the square root of 32. And that's completely different from the square root of 3 times the whole number 2. So to avoid any confusion or uncertainty about that, we always write the whole number in front of the square root number. Okay? So just a sort of a reminder now about the fact that the whole numbers 2 times 3 can be simplified, they can be combined. You get a simplified result, 6. Square root of 2 times the square root of 3 can be combined, and you get a simplified result, the square root of 6. But a whole number times a radical number, like 2 times the square root of 3, well, that doesn't get simplified. It's just 2 radical 3. Just like 2 times 3 is 6, and x times x is x squared, but 2 times x doesn't really get simplified. It's just 2x. Okay? So back in the day, when you were first learning algebra, and your algebra teacher may have asked you, what's 2 times x? You remember this day? Your algebra teacher asked you, what's 2 times x? And everybody in the class just gave the teacher a blank stare and thought, what? What are you talking about? What's x? And all the algebra teacher wanted you to say was 2x, right? The algebra teacher may have thought that was simple and obvious, but really that's a hurdle you've got to get over in your mind, right? And you probably got over it fairly quickly and easily. Still, it is a little bit of a mental hurdle. Well, same with 2 radical 3. You've got to realize that there is a multiplication symbol, an imaginary multiplication symbol in between that 2 and that radical 3. Okay. All right. And I want to say this for the sake of thoroughness. You might hear occasionally, if a teacher is a little careless, they might say, you can't multiply 2 times the radical 3. You can multiply 2 times 3. You can multiply square root of 2 times square root of 3, but you can't multiply 2 times the whole 2 times the square root of 3. Well, yes, you can. Okay, anybody who says that is being very careless, and they're confusing you. You can multiply 2 times the square root of 3. What do you get when you do that? Have you been paying attention? What do you get when you multiply 2 times the square root of 3? You get 2 square root of 3. Okay? If a teacher says to you, you can't multiply 2 times the square root of 3, what they mean to say and what they should be saying is you cannot combine the 2 times the radical 3 and get a more simplified result. Okay? But you certainly can multiply 2 times the square root of 3. Okay? That's the same as if you said, can you add the terms 2 and x? And you might say, no, they're not like terms. And I would say, yes, you can add 2 and x. What you get is 2 plus x, okay? What you can't do is you can't combine the 2 and the x with addition to get anything more simplified, okay? I think that's important. Keep that in mind so you're not confused. Let's move down. Write all the perfect squares less than 150. You may not be familiar with this phrase, perfect squares. It refers to numbers that you get as a result of squaring nice whole numbers. So the whole number 1 squared is 1. That's the first perfect square. The whole number 2 squared is 4. That's the next perfect square. 3 squared is 9. That's the next perfect square. Are you already ahead of me on this? Do you remember your times tables? Right? This is a good exercise, really, for what we have to do in the immediate future here. I know you can reach for a calculator and punch all these numbers in, but it would be good for you to try to think these through. This is 3 squared. What's 4 squared? And 5 squared? And 6 squared? 7 squared? 8 squared? 9 squared? 10 squared? Come on, if you learn your times tables, you probably learned them all the way up through 12 times 12. So what's 11 times 11? Actually, we did that on the previous page. And then 12 times 12. Okay. It's helpful to know these numbers, to just know them. It's not necessary. You can always crank them out of a calculator. Okay. But it's helpful. It just makes your work go a little faster sometimes. Like for the problems that we're going to do here, we want to now simplify these expressions. And again, simplifying does not mean turning it into a decimal and approximating it. Okay. You can't simplify square root of 40 with your calculator. You'll get a decimal. The decimals will run on forever. They'll never repeat. If you write down some decimal answer, you've thrown away digits and you do not have the exact value that you started with. So that's not acceptable. Okay. Nonetheless, there are ways to simplify square root numbers, even when they're not nice whole numbers. And the way we do that is by rewriting the expression as an equivalent value, but with a smaller square root number as part of it, the smallest square root number that we can possibly get out of it. Let me show you an example from the previous page. See, we started here with this number, the square root of 12, and we rewrote it as the square root of 3 times the square root of 4. Then we changed the square root of 4 into a whole number 2, and eventually rewrote this value, square root of 12, as 2 square root of 3, or 2 times the square root of 3. This would be considered a simplified version of the square root of 12 because we have reduced the square root number part as small as we can possibly get it. Now we've got a whole number in front of it, and so, you might argue that, hey, 2 times the square root of 3 actually looks less simplified, more complicated as a mathematical expression to me, Mr. Nortillo, because that's got a multiplication and a square root in it, whereas the original expression didn't have the multiplication at all. It just had the square root. How on earth is this simpler? Well, in that case, you're probably using the word simple in a more of an everyday context, okay? Or a layperson's context, a layman's context, not a mathematician's context, okay? When we talk about simplifying square root numbers, we're not necessarily talking about making the final expression look simpler, but what we mean is sort of squeezing down that square root number to be as small as possible and popping out of that square root number a whole number of some size. So how could we do that? Well, we do it by factoring the original square root number. Square root of 40 could be factored. What are factors of 40? Well, 1 times 40, sure, but let's start with 2 times 20. Okay. But there's other factors of 40. There's 4, square root of 4 times square root of 10. And then there's, square root of 5 times square root of 8. Okay. Now, none of these results are yet simplified versions of the square root of 40. We say mathematically that we cannot simplify square root of 40 unless we can somehow extract a whole number out of that square root of 40 term, okay? And none of these are whole numbers. Square root of 2, square root of 20, square root of 4, square root of 10, square root of 5, square root of 8. Those are all just more square root terms. But one of those square root numbers could itself, just one of them, could be now turned into a whole number. Do you see which one? It's the square root of 4, right? square root of 4 is exactly the whole number 2. So now that square root of 4 can become a 2. The square root of 10, that's not a nice whole number. Okay. I'm not going to write the multiplication symbol in between. I'm just going to leave it as 2 radical 10. So now we have reduced the square root of 40 to the square root of 10. We've gotten that number inside the square root symbol, which, by the way, we call the radicand. That's the name for that number inside the square root symbol. We've gotten that radicand to be smaller. We've got a whole number on the outside. This is considered a simplified version of the square root of 40. Okay. Now there were 3 sets of factors of 40. There was the 2 times 20, the 4 times 10. Remember a moment ago we had the 5 times 8. As it turns out, though, this set of factors here, while it's true, it is not helpful to us in trying to simplify the square root of 40. Okay? Sometimes on a quiz, I'll put simplify square root of 40, and occasionally I'll have a student write something like square root of 2 times square root of 20, and they'll circle that. That is not a simplified version of the square root of 40. Okay? Because again, the objective is to get a whole number out of that square. If you cannot get a whole number out of it, you can't simplify it. You just say, well, this is already simplified. Okay? How about square root of 54? There's lots of factors of 54. We could do square root of 2 times square root of 27. Okay? But unless one of those turns into a whole number, that's not helpful, right? Are either one of those numbers 2 or 27 in this list of perfect squares? See, if they're not in this list, they're not helpful. That's why it's helpful to know this list of perfect squares. Well, neither one of those shows up, so that's not helpful. Okay. Well, you might not know this, but you could check it with your calculator. If you're not sure what all the factors of 54 are, you just start with 2, divide 54 by 2, you get 27, divide 54 by 3, guess what? You get 18. Are either of those numbers on that list of perfect squares? No, not helpful. Okay, so now you can try 4, 54 divided by 4. Oh, you're going to get 13.5. So 4 is not a factor at all. You could try 5, but you probably know 5 is not a factor of 54. Then you could try 6, and you would find out that, yes, 6 times 9, if you didn't remember. Are either one of those numbers on the list? Yes. Which one? I'm talking about the list of perfect squares across the top of the page. Is the 6 or the 9 in that list? The 9 is, right? What is the square root of 9? It's 3. Okay, so now we've managed to extract a whole number out of the original square root of 54. But you don't want to leave your answer like that because we always like to write the whole number in front. And then there's no need to put the multiplication symbol in between. Okay? Square root of 500. Oh my gosh. There's lots of factors of 500. And you could start, with your calculator, 500 divided by 2, by 3, by 4. You'd find lots and lots of factors. But come on, isn't there a fairly obvious number in this list of perfect squares, which is a factor of 500? Well, there's more than one number in this list, which is a factor of 500, but I think the most obvious one and the largest one is 100, right? Square root of 100 times the square root of 5. 100 times 5 is 500, and the square root of 100 is 10. So there's the simplified version of the square root of 500, okay? Square root of 30. Square root of 30 has several pairs of factors. Square root of 3 times square root of 10. Oh, I skipped over square root of 2 times square root of 15. And then there's square root of 5 times square root of 6. But none of those numbers, none of them, are in the list of perfect squares. None of them can be converted, so to speak, into a whole number. And so this square root of 30 is already simplified as much as possible. It cannot be simplified anymore. I mean, I would accept any of the following answers to the problem, simplify square root of 30. I would accept you saying it's already simplified. I would accept you saying it can't be simplified anymore. Or I would accept you just writing square root of 30, which implies that it is as simplified as it's going to get. Okay. Same with square root of 42. Square root of 42 could be 2 times 21, could be 3 times 14, could be 6 times 7. None of those square roots turn into a whole number. So this is already simplified again. Okay, how about square root of 64? Well, that's just 8, right? Come on, you got to know your perfect squares. Of course, you can always check in a calculator, punch in square root of 64, right? All right, now, square root of 108 is a more complicated example than any of these. I've listed it out 3 times, and I've solved it 3 different ways. And I actually want to put that yellow highlighted line there. It shows us 3 different answers because square root of 108 can be factored into 3 times 36. And the square root of 36 is just 6, so you get 1 answer here. Square root of 108 can also be factored into 4 times 27, and then the square root of 4 becomes a 2. So we get 2 times square root of 27, or square root of 108 is also square root of 9 times square root of 12, and the square root of 9 becomes a 3. And so we get 3 times the square root of 12. So on that yellow highlighted line, I have 3 different answers. They are all simplified versions of the square root of 108. But here's the problem. Only one of them is acceptable because only one of them is the most simplified. Okay? 2 out of those 3 answers can be simplified some more. It's sort of like reducing a fraction. If I gave you the fraction 18 over 24, and I said reduce it, and you reduced it to 9/12. Okay, well, partial credit maybe for reducing, but not full credit because you didn't reduce it completely. Or you might reduce 18/24 if you divide both numbers by 3 to 6/8. Okay, yeah, that's reduced, but not completely. Both the 9/12 and the 6/8 can be reduced to 3/4, which is the only acceptable answer if I say reduce 18/24 completely. Okay, so if I scroll down a little bit, you can see that if we get an answer of 2 times the square root of 27, you've got to recognize, and this really only comes with practice, you got to recognize that the square root of 27 by itself could be reduced some more. See, it breaks up into the square root of 9 times the square root of 3. The square root of 9 becomes a whole 3. Notice in that second to last line there, I've reinserted a multiplication dot between the whole 2 and the whole 3 so that it doesn't look like 23, right? Because in this line right here, this is 2 times the square root of 9 times the square root of 3. And so that multiplication needs to be preserved, or at least the awareness of it needs to be preserved by putting that dot in the next line. And then the whole number 2 and the whole number 3, they can be remultiplied together, recombined to get a whole number 6. And now we have an answer that matches the one on the left. Same thing with the square root of 12. Can be split up into square root of 4, square root of 3. The square root of 4 becomes a whole number 2. I reinsert the multiplication dot between the 3 and the 2, and then recombine through multiplication the whole 3 and the whole 2 to get a 6. So occasionally you run into this sort of thing. Quite honestly, this year, this is not something that I really want to torture you with. We may see it happen occasionally. There might be a problem on a quiz where you have to be careful about simplifying completely and not just partly. Okay. There are a couple problems like this in the homework tonight where it's possible for you to simplify or reduce the number without reducing it all the way. I've got all the answers worked out, and I've got some additional notes about those problems in case you get a less than completely simplified answer. Okay. Last few problems we want to work through here in preparation for not just the homework tonight, but for the problems we're going to be doing in the next lesson. Well, not the next one, but very soon in this chapter. We're going to get back to geometry soon. We're going to need to know how to simplify expressions like the ones here below. Okay, so once again, whole numbers can be combined through multiplication, but a whole number times a radical number just remains the whole number times the radical number. Radical numbers can be combined through multiplication, but then the whole number times the radical just remains as the whole number times the radical. Now, if that square root of 30 could be simplified anymore, then we should do it. But I think we already talked about that particular example. That doesn't get simplified anymore. How about squaring 10 radical 3? I'm going to do this the long way, and I'm going to encourage you to do it the long way when you work out problems like these on the homework. After some practice, you really start to see the patterns. You don't have to do every one of the steps that I'm going to show you here, but to make sense out of it and to ensure that you do these problems correctly, I would encourage doing this. Recall that squaring something is multiplying that something. Here's that something that's inside the parentheses. We're going to multiply that whole thing by itself, right? So we're going to multiply 10 radical 3 times itself, which is another 10 radical 3. Okay, that's the first baby step, recognizing that squaring something is multiplying it by itself. So we kind of expand it out a little bit. Now here's the next baby step. Recognize that between the 10 and the square root of 3, there's an imaginary multiplication symbol. Okay, and likewise between the second 10 and the second radical 3, there's a multiplication symbol in there. So really what we have now here are 4 numbers all being multiplied together. Okay. Now, does it matter what order you multiply numbers in? Are you going to get a different answer if you do 3 times 5 or 5 times 3? Do you get different answers? No, you don't get different answers. You can change the order of multiplication any which way you want. You're going to get the same answer. So I'm going to change the order in which these 4 numbers are being multiplied. I'm going to write that first 10 first, then I'm going to write the next whole 10. Then I'm going to write one of the radical 3's and then the other radical 3. Okay? And now I'm going to start multiplying pairs of numbers, because really, nobody can multiply more than 2 numbers at a time anyway, right? Well, what is the 10 times 10? Those numbers can be combined, and you get 100. And then there's a multiplication. And then what is the square root of 3 times the square root of 3? Those numbers can be combined, and you get square root of 9. Or maybe you were thinking that's 3, and you'd be right. Square root of 9 is 3. Right? So now we get 100 times 3. And now those 2 whole numbers can be combined through multiplication to get 300. That is the final, most simplified version of the original 10 radical 3 squared. Okay? We'll do one more example much more quickly in the same way. 3 square root of 5 times 3 square root of 5. Now rearrange the order, which, after you've done a lot of these and you've practiced it and you can sort of do this in your head, you can rearrange the order of these terms. Then the 3 times 3 is 9. Square root of 5 times square root of 5 is square root of 25. But hey, the square root of 25 is just 5. And then finally recombine the 9 times 5 into 45. Okay? So that's it. You got some homework to do. Be ready next time we meet.